All right, so I think it's 12:05, close to 12:05. So I think we can start. Hello, everyone, and thank you so much for joining in to the Grundfest Memorial Lecture for this month. Before starting out with a speaker, I'll just give a few beginning notes and then pass over the mic. So just to recap, if any of you are attending the lecture for the first time, we typically start the lecture at 12:05 as we are now, just to allow everyone to come in. And the lecture goes until 12:50, after which we have some question answer rounds. Please also follow the lecture series webpage to continue getting updates as to our upcoming speakers. That being said, the Grundfest Lecture Series is named after Professor Warren Grundfest, who was an SPI fellow in biophotonics and a professor at UCLA. He was a pioneer in many imaging modalities, and most importantly for our context, he was a great advocate of junior scholars, which is also the purpose of this lecture series, to provide a platform to early career and late stage PhD students. I would also like to extend my greatest thanks to my co-organizers, Professor Ashita Kadambi and Professor Katie Bowman, for helping and for essentially organizing this entire lecture series, which is amazing. And finally, we'd also like to thank our sponsor, Akasha Imaging, who have been very gracious in sponsoring an inverse honorarium for non-permanent speakers, just as a very small incentive, as additional incentive to participate in this lecture series as well. And with all that being said, it's my great honor to it's all a great honor to have Kristina Monakhova speaking to us today. Kristina will be talking about her amazing recent work on low-light video denoising using physics-informed noise models. So without further ado, I'd like to pass over the mic to her. Thank you.
Thanks for the intro. Let me go ahead and share my screen. Okay, can everyone see that okay? All right, so I'm really happy to be here today and talk to you about my most recent work on video denoising and starlight using a learned physics-informed noise model. And let's go ahead and begin. So basically, if you take the very best cameras that we have available today, they have a limit, and the limit is they need enough light in order to see the world. And currently, that limit is that the moon must be out. So there's this show on Netflix called Night on Earth, and they have these amazing clips of these animals moving around at night. But of course, they had this problem where, you know, if the moon was out, they could film the animals and get these amazing clips. But if the moon was not out, it was just too dark and they couldn't see anything. So the question we had for this project was, well, can we take like the best cameras that we have, and then can we do some sort of clever algorithms to really break this limit and push the limits of what we can see? So the question was, can we achieve photorealistic videos in starlight with no active illumination? So we want to go somewhere basically on a moonless, clear night with no flashlights, no lights whatsoever, and see if we can film things at night and get back these photorealistic videos at sub-mililux levels of illumination. So there's very, very little light in the scene. Now, the approach we have for this is we assume that, okay, perhaps we can take some kind of really great camera, and then perhaps we can take these like very, very noisy, high gain videos, and then using the most recent breakthroughs in denoisers and machine learning, perhaps we can make some kind of denoiser that's going to work really well for these very, very low light videos, and hopefully get out these photorealistic videos at night for the first time. So there are several components to this. And the first is that, well, we need to have a really good camera. And so the question is, well, what is a really good camera for nighttime videography? And really the answer here is that we need to have a camera that can capture as much light as possible. So what that means is we need to have very large, very sensitive pixels on the camera. We need to have a very good lens that has a large aperture so we can collect as much light as possible. And also it's been shown that at night, whenever the moon is not out, whenever you have just starlight, most of the wavelength of light is actually in the longer wavelengths. So if we have some IR sensitivity, we can do a lot better because there's a lot more in the IR spectrum than in the visible range. So hopefully we can have a camera that is sensitive to a little bit in IR as well. So luckily, there actually exists on the market a camera that satisfies all of these. So we have this great camera that we're using that has massive pixels. They're 19 microns in size. And we have a really good lens that has a very large field of view, so we can hopefully see the night sky and some motion, and it has a very large aperture. Now, this camera is also has kind of a special arrangement, which is that instead of having a typical Bayer pattern, which has red, green, and blue pixels, we have this additional IR channel. So rather than having like these 3 color channels, now we have 4. And so we have IR sensitivity here. Now, the thing that's also interesting about this camera is that actually, if you take a look at the response of each filter, so for blue light, you have a peak at the blue wavelengths and then a peak in IR as well. Same for green and same for red. So every single pixel on this camera is sensitive in IR. So that means we're going to be able to capture as much light as possible from the scene. But then, well, if you want to get back a color image, what you have to do is you have these like 4 channels. You have to subtract out the IR to get back your RGB image. Okay, so we have a camera. It seems really good on paper. It satisfies all of our constraints and it seems like it should do really, really well in low light settings. Now the question is, how well does it work? Can we actually see anything? Well, before we can actually answer that, we have to find a place where we have sub-mililux levels of illumination. So that means we need to go somewhere on a moonless, clear night. And well, if I were to go out in Berkeley, there's a ton of light pollution. So I mean, we're never going to achieve sub-mililux levels of light. So actually, we had to go kind of to the middle of nowhere to this place called Point Arena, California. And I chose this because if you look at a light pollution map, and in this map, basically, the brighter whites and reds show a lot of light pollution, like places around the Bay Area. And the darker colors here, like black and blue, show very, very dark places at night. And so we found a place that's, as dark as possible while still being fairly close to Berkeley. And then, so it seems like this is a good candidate location where perhaps there's no glow from city lights at night, and there's very little light pollution. So hopefully we can actually achieve these very low light levels to take our data. But of course, we have to verify this. And so we have this ground truth photometer, which is going to basically measure how much light is present in the scene. This is going to verify whether we are indeed in such a dark condition or not. And so we had one of these, and basically throughout the recording, we can measure that we're between 0.6 and 0.7 mililux of illumination. So we are indeed under 1 mililux of illumination, and we are indeed like a very, very dark regime. And so given this, I was able to then take some videos, and then we can finally answer this question of like, okay, how well does this camera on its own do in such light conditions? And here's the result. So basically the raw video clip from this camera at the very darkest setting with no moon present by just the light of the stars is as follows. you can see a little bit of motion. You can see kind of the Milky Way and the stars in the background. This is very promising. And if you contrast stretch the video a little bit more, you can see actually quite a bit of signal. So, I mean, you can see this volleyball, you can see details in the shirt, but of course, you also see a lot of noise. And so we have this issue where, okay, these clips, because we are taking this camera and pushing it to the limits, we have this very, very high gain setting. And with a very high gain setting comes this trade-off of having a lot of noise. And this noise is kind of strange. It doesn't look very Gaussian. We have all of these these lines showing up, and has a lot of structure in it. But I mean, I think this is a good first step. We can see that there is some signal here, and we can hope to actually maybe denoise this and get back some good videos. So now the next question is, all right, so we have some videos, they look promising, but what is a good denoiser for these very low light videos? And I mean, denoising has been around for a very long time. There's a whole bunch of options we can choose here. And I'm going to kind of break down all of the research and denoising onto this scale of more classic denoising to deep learning based approaches. Now, so on the classic side, we have these heuristic methods that you can use usually off the shelf. They don't require any sort of training data, and some of them are actually designed for videos, so they can handle dynamic scenes really well. However, I mean, more recently, it's been shown that some of these methods have been outperformed by deep learning based methods, and they can be sometimes a little bit slow. So, okay, well, we have these methods, we can see how well it does in this low light regime. And to do that, basically, we're going to just like take one of these denoisers called VBM40, which is a state-of-the-art video denoiser from the classic methods, and apply it to our videos. And here's what we see. So, the video looks a little bit better. However, unfortunately, you can see that there's still quite a bit of noise here. So if we zoom in, you can see all of these lines and all of these artifacts, and well, basically the denoiser fails. And one of the reasons for this is that most of these denoisers assume IID Gaussian noise. But as we saw before, we clearly don't have that. We have this more structured noise. And so these classic methods, they completely fail on this problem. I think someone maybe is unmuted. But okay, so now, so we try these classic methods, they don't work. Let's see if we can go down this spectrum of denoisers and try something else and see how it does. So another method that we can try is unsupervised or self-supervised learning, where here it's also very nice because you don't need any training data. And basically what you can do is you can try to denoise the image using the image itself. And there's been a number of methods that have proposed this over the last few years, like deep image prior, noise to self, noise to void, and all these methods. And so, we were wondering, can we apply one of these off the shelf and see if it'll work on our, very noisy images and videos? And so if we have like a raw image like this, unfortunately, noise to self also completely fails in this setting. And if we zoom in a little bit closer, you can see we still have like all of these lines present. And one thing that I suspect is happening here is that these methods also assume IID Gaussian noise typically, and our noise is not independent necessarily. We have a lot of structure here. We have a lot of these line artifacts that we see. And so it's hard for these methods to distinguish like what is signal and what is noise. And so I think what it's doing is it thinks that like these lines are part of the signal whenever they're not. So basically these unsupervised methods don't work so well in this regime either. So let's go on the other side of the spectrum to the deep learning based approaches. So on this side, we have supervised learning, where basically you can have like a real data set from your camera of noisy and clean images, and you can train something to try to do the denoising for you. And this has seen a lot of success in extreme low light imaging, such as in learning to see in the dark. And so this seems like a promising approach, and let's take a look at how it works. Basically, the idea here is that we're going to take our camera and we're going to take a high gain, short exposure image, which is going to give us our real noisy image. And then we're going to take this low gain, long exposure image, which will give us this clean, noiseless image. So if we can take a bunch of data like this and have a training data set, we can then basically have a denoising network, which will attempt to denoise the image, and we'll compare against the real noiseless image through our loss and update the network as we go for all of our training data until hopefully our network is able to denoise the images really well. And I mean, so we actually tried this. So we can take a data set of still images with like high gain, low gain, and train a network like this and see how well it does. And here's the performance. You know, it's a little bit better, but however, we see a lot of these flickering artifacts, and things are kind of like popping in and out. And, you know, there's not a lot of detail here. It's all kind of like blurred out and washed out. So one of the reasons for this is that, you know, we want to do video denoising. So in this sort of approach actually just takes an image and looks at it like one image at a time. And so a lot of things don't change throughout the video. Like a lot of the background might stay the same. So it's kind of a waste to take a look at a single image at a time instead of trying to like denoise this whole video together, because then you can use information from all of these images to get your best estimate. So this method doesn't really work. And well, the question is, can we, instead of doing like this single image denoising in a supervised way, can we instead do it for videos? However, this has a problem where you still have to take this like high gain, low gain video data set. But now, I mean, how do we do this? Because the problem is, you know, we want to image videos with motion in them. And so now, you know, unfortunately, you cannot take this sort of data set because it's not going to be aligned. There's going to be motion, and you cannot really have this like aligned data set to do this with, unless you have a lot more expensive hardware. And so this is not very practical for our situation. And so basically, you know, this sort of supervised approach isn't going to work for us. So what's left? We went from classic denoising to the very, very deep end, and nothing seems to really work. But fortunately, there's one more option, which is the following: simulation supervised learning. So rather than taking a real data set of noisy and clean images, what we can do is we can say, okay, well, perhaps, you know, if we have a good way of modeling our noise, we can take some like clean videos and then maybe simulate a bunch of noisy videos. And this can be really, really nice because you don't need to take like this large real data set of videos. As long as you have a good way to generate synthetic noisy videos, you're all set. So we're gonna take a look at this approach and see how far we can push it. So basically, the way it works is we need to have some sort of clean, noiseless videos with motion. We're going to need some sort of way of modeling our noise. This is going to generate some noisy video clips. And then using that, we can then train our denoising network to hopefully produce like a denoised video and compare that against the clean video with the loss, and update the network until we do really well. And hopefully, if we can train this in simulation with a really good noise model, hopefully it'll work on some real experimental noisy clips from our camera. Now, there's a whole bunch of deep learning based methods that basically use this approach. However, one thing that they do is they assume that the noise model, once again, is Gaussian. So if we take one of the state-of-the-art denoisers that's been trained on Gaussian noise and apply it to our data, it doesn't really work. You still see all of these line artifacts, and there's like a lot of detail that's lost here, essentially. So that just goes to show us that for this sort of method to work, we really need to have a very good, very accurate noise model. Otherwise, we're going to be out of luck. So, I mean, that brings us to this question of like, how do we model this extremely high gain, low light noise. And well, I mean, typically you might model noise as Gaussian. Unfortunately, of course, as we've seen over and over again, our noise doesn't look like Gaussian noise. So here's like a real noisy image in the middle here. And here's the Gaussian noise on the right. It looks very, very different. So there's another paper that came out recently that basically uses this low light model that is calibrated from the camera. So you can basically fit a bunch of parameters by hand using some calibration images and try to create this like really accurate low light noise model for your camera. And so we tried this out. And unfortunately for our case, it doesn't look quite like the real noise. It comes much closer. So you can see some of these lines are more accurate, but it doesn't really match the real noise. And if you can't get a noise model that's very, very accurate, we're kind of out of luck. We can't train our denoiser. So we had this question of like, all right, so none of the off-the-shelf noise models work for our case. What can we do? And so one thing that we thought of is, well, perhaps we can learn a noise model. We have already a data set where we have some clean images and noisy images. Maybe instead of training a denoiser, we can train a noise model that does the opposite. We go from a clean image to a noisy image. And then, well, perhaps we can then, compare the generated noisy image to the real noisy image, somehow take the loss, update our noise model until we get very accurate noise. Well, unfortunately, noise is stochastic. So if we try to do this, every time you might have like a very different sort of noise that you see. So if you're taking like a pointwise loss, like mean squared error, for instance, you're going to get a very different answer every time. So unfortunately, this sort of like supervised approach doesn't really work for learning a noise model. So what can we do? Well, our answer was we can instead use a generative adversarial network, again, to try to learn this noise model. And what this does is, instead of just trying to take the loss directly, is we now have two networks. We have our noise model, which we're going to call our generator, and we have our discriminator. And so basically, the generator is going to take our clean image patches and try to generate plausible, realistic, noisy images. And then the discriminator is going to be tasked with classifying whether the noise is real or fake. And so we're going to have our real noisy images going to the discriminator as well. And so basically the discriminator is going to take the form of like a classic, basically just going to classify whether the noise is real or fake. And the generator is going to try to compete with the discriminator. So basically you're trying to like have the generator fool the discriminator into making very, very realistic noise. And so basically, hopefully, if this all works well, once training is complete, the generator should make noise that is indistinguishable from the real noise, and it should be able to fool the discriminator about half the time. Now, so the problem here is that, well, if you look at works, at some of the work on GANs, they're kind of known to be notoriously hard to train, and they're very good at hallucinating things. And so we want this to be easy to train, and we want this to be as physically interpretable as we can make it. And so actually what we're going to do here is we're going to constrain the generator to have some physics-based noise parameters followed by a CNN, which is going to refine that guess. And the way we do this is basically we say, all right, we'll have just a few parameters that the generator is going to be learning from the data. And those parameters are based on some known low light noise parameters for CMOS cameras. So for instance, we have this like read and shot noise. And what we're going to do is we're just going to learn the standard deviation of these two values. So we just have these two parameters here that we want to learn. Same for some other components of noise. Like we see these sort of like these row artifacts. And this is actually a known phenomenon at very high gain. You might have these random row offsets in your camera. And so here we're actually just going to learn the standard deviation of those random row offsets. And so basically we're going to like have these random distributions, and we're going to learn a single parameter of those draw from those to generate some realistic noise. So we could stop there. We could just parameterize all the most common components of our noise and try to get back a really realistic noise model. And we've tried this. However, we found that it works better if you, in addition, include some sort of CNN at the end with a few more learnable parameters. And the goal of that is basically just to refine the estimate of the noise and make it as good as possible. So one example is that, here we're using this read and shot noise model that assumes sort of Gaussian read and shot noise. However, for low light conditions, it might be closer to Poisson noise. However, Poisson noise doesn't really work well on this sort of setting because you can't really easily differentiate through it and learn the parameters of it, whereas you can for Gaussian noise. So the UNet here is in charge of basically, accounting for any errors in our modeling of the noise and just trying to further refine our estimate and account for anything that we don't model in these physics-based noise parameters. So we have this kind of combined approach where we have a few physics-based parameters together with a UNet. And basically we're going to, learn all of these parameters together based on a few images from our training data to try to create the most realistic synthetic noise that we can. So how does it do? Well, as you saw before, if we have an input image and some real noisy image, the Gaussian noise model, it doesn't do so well. The low light model also doesn't. However, our learned model does a lot better and is much, much closer to the real noisy image. So if we have another example of this leaf, you can see the real noise in the middle and then the Gaussian model on the right, the low light noise model on the right as well, and then finally ours. So as we can see visually, at least, it looks like we are doing quite well. We are able to at least visually achieve something that looks very similar to the real noisy images. We can look at the distribution of the noise to further quantify this. So if we have our input, we have our real noise, then the Gaussian low light noise in ours, we can see that the distribution of pixels in this noise actually looks a lot more similar. So we're matching this quite well. Now we quantified this using KL divergence, which is a measure of how close two probability distributions are to each other. And we basically even went a little bit further and said, which parts of our noise model are contributing the most to this? And can we just use a certain part of it? So here we have different parts of our noise model. And as we add more and more components, it gets better and better. We get a lower KL divergence. And so finally, the full model achieves the lowest KL divergence. Now on the top here, we compare against some other learned noise models, but these are all just purely deep methods that don't have any physics-based parameters. So here we're kind of showing that, if we have these physics-based parameters, we're able to basically decrease the search space and make this problem a whole lot easier to solve and get back a very good result. Now, the other really cool thing about having these physics-based noise parameters is after the network is done training, we can actually check and see what it's learning. So for example, if we have a clean image on the left here, we can see that the read and shot noise produces some noise like this, where it depends on the intensity of the image. And so you can see that there's kind of more variance in the noise as the intensity is higher, which is what we expected for it to do basically. We have some quantization noise here. We can see some row noise as well, which is adding this random row offset, which you see in the noise on the right. And I mean, finally, one last thing is we actually included this fixed pattern noise, which we did not learn, but we just calibrated from the camera. And this is noise that we see across multiple frames of the camera. So if we look at the distribution, you can see how it changes as you add all this noise. And actually after the CNN, it tends to kind of push the image so it's a little bit lower, so the light is a little bit lower intensity essentially. And finally, after we clip it, you can see that the generated noise is very similar to the real noise. So we can kind of visualize how different parts of our noise model are working together to create our final estimate of the noisy image. Okay, so now we have a noise model. Now we want to do the actual denoising. And so basically we can take these clean videos, run them through our fixed noise model, generate some noisy videos, and then hopefully train our denoiser to denoise these videos, compare them against the clean videos, and update this until we have a really good denoiser. So for video denoising, you need a whole bunch of data. So we're going to use 3 sets of training data for this problem. The first is going to be some videos from an online data set called the MOT data set. And we have these RGB noiseless videos, which we're then going to use our noise model to create these noisy videos from. However, one problem with this training data set is all of these online images are RGB. And as you saw before, our camera has an extra IR channel. So the colors are a little bit off for this. So basically we use this data set for some pre-training, but for the fine tuning, we don't use this because it's going to lead to some issues in the colors for the denoiser. So besides this data set, we use 2 additional sets of data. First is we use some noiseless videos with a lot of motion from our camera. And as before, we apply the noise generator to generate some synthetic noisy clips with a lot of motion in them. And we also, because we already have this data set of still images from our camera, we're going to use that. We're just going to use that as well, because, you know, we have these like noiseless still images, and we have like the real noisy stills from the camera. So we might as well use this information. So, okay, we basically have these 3 sets of data, some data from online, then we have some real clips that are noiseless, and then some real clips that are noisy and noiseless as well, but have no motion in them. Okay, so now let's take a closer look at our denoiser. So we chose to use a denoiser that works really well for videos, and it's based off of this network called FastDVDNet, but we modified it by using these HR networks inside of this. And so this is just like a state-of-the-art sort of thing we can use that works pretty well for our images. So basically, we process 5 clips at a time to produce a single image in the output. And we kind of have this like sliding scale where we process like 1 image at a time to produce our video. And as for post-processing, we don't do anything fancy here. We just do some simple gamma correction, white balancing. And so there's actually a lot of work that could be done in the future to improve the post-processing. Okay, so we have our video denoiser. It's trained. Let's see how well it performs on some still images. Because for the still images, we actually have some ground truth we can compare it to. So here's an example of a raw, noisy image. And we can apply all of those other methods to it and see how it does. With VBM4D, we have a lot of lines. With this FastDVDNet, for a Gaussian noise, it's a little bit blurred out. For learning to see in the dark, using our own data, it does quite a bit better. And then finally, for our method, it does the best. So you can see here, for this method, you don't see the details in the letters, whereas for ours, you do, and you get very good image quality. If you compare it to the ground truth, it's very close. And you can see that we're getting most of these details here. Here's another image. Here's the initial raw noisy image. You can see VBM4D, FastDVDNet, learning to see in the dark, and then ours. And once again, you can see that we're achieving much better image quality along these letters here. So you actually can see these letters in the cans, whereas you can't see them in the other methods. And it's very close to the real ground truth. So that's kind of a proxy for how well we're doing. We can see that we're doing really well on these 2D images, but you know, the real test is how well can we do on dynamic scenes? And for these, there's no ground truth available. And so now I'm going to show you some video clips that were taken in the darkest settings with no moon out, just by the light of the stars, essentially. So you can see the raw video here. Then if we contrast stretch it, you can see all of the noise that's present in this video, and it's extremely noisy. With VBM4D, it does a little bit better, but there's still all these lines present. With learning to see in the dark, there's all this flickering that we saw before. Then with fast DVDNet with the Gaussian noise, you still see all these lines and it's very blurred out. And finally with ours, we're able to have very, very good video quality where you actually see the shooting star here and you see a lot of the details in this cactus and these flags waving around. And so we're able to actually achieve photorealistic videos in these very extremely dark settings. One thing that's kind of cool is I can actually play a longer clip here. And one thing I want you to notice and pay attention to is if you take a look, we can actually see some satellites moving through the sky. So this clip's going to play again. And basically, if you pay attention, you can see this little point moving across the sky. So this is taken at about 8.5 hertz. And so, we have enough video resolution to, see these satellites moving across the sky, and we can actually see a shooting star. So I think this is really exciting. Actually, I'm going to scroll through this real fast so you can see the motion. So you can kind of see the motion of the satellites. And then we also the video is fast enough to also catch the shooting star here as well. So I think that this is really cool because, typically if you do any sort of photography at very low light settings, normally you'd have to go in and take an exposure that's about 30 seconds long to see all this detail in the sky. And here where we have a whole video. And so I was really excited by this result. So besides just some images of flags waving, we can also take some dynamic videos with a lot more motion in them. So you can see here, this is the raw clip with a person with an umbrella spinning. And after processing, we can actually see another shooting star here. We can see the Milky Way in the background, and we can see all of the motion of this umbrella. And we can see even more things. We can actually take videos of people dancing by the light of the Milky Way. And so you can see the Milky Way and all the stars in the background, and you can see these people dancing around. And it's kind of hard to appreciate this because whenever we actually here taking this data, we couldn't see anything. So our eyes were not good enough to really see. So we're kind of all just dancing in the dark essentially. But with this camera, we can then do some processing and actually get back a lot of details. So I have a clip just combining a few different videos that we have. And once again, we can see a lot of motion. We can see this volleyball moving, these people dancing, and all of this great detail by the light of just the stars with no external lights. All right, so that brings me to towards the end of the talk. Basically, we showed photorealistic videography in sub-mililux for the very first time. We actually have an open source data set of all of the videos, which are available on our project page and data set, which is, there's a link to it on the bottom here. And I think what's really exciting is we showed that, we can take a camera and we can push it beyond its normal operating range by using this GAN-tuned physics-based noise model. So using a little bit of data from the camera, which is actually very, very easy to obtain. You just have to automatically set it to take a few high gain, low gain images. You can then use that to calibrate a very, very accurate noise model for the camera, which you can then use to basically push this camera beyond its limits. So I think this is very exciting for a whole number of different applications potentially. So there are, of course, some limitations to this work. For instance, all of this was designed for a specific camera gain, basically the highest gain on the camera. And so there's this question of can you actually calibrate a general version of this, which will work for any arbitrary camera gain or camera setting? So I think that's a very exciting question. And perhaps in the future, we can have a general calibration that you can take, and then you could have a really accurate noise model for all of your camera settings. And then of course, we showed this for some videos at night, but there's a question of like, there's a lot of different applications that are photon starved. So for instance, in microscopy, maybe astronomy. So I think there's a lot of potential of trying to like push our cameras to their limits, and using very good denoisers to get back some content from these. And so of course, then the other question as well. So I showed this documentary of animals at night. So, you know, perhaps in the future, the image quality is going to be good enough that perhaps we can actually film animals by the light of just the stars well enough that we can actually like make some scientific discoveries and discover some new animal behaviors at night. And so, yeah, basically, I'm really excited for the future of this, and I think there's a lot of potential. And using basically GAN-tuned physics-based noise models for cameras, trying to push cameras to their limits. I'd like to acknowledge my co-authors. So this work is based on a paper that's going to be appearing at CVPR, and it was done while I was at Intel Labs and also at Berkeley. So it's a collaboration between the two. And with that, you know, I'd like to just show this video clip and see if there's any questions anyone has. So yes, I'm ending a little bit early.
Okay, great. Thank you so much for the talk. Really appreciate it. So you can see our virtual reactions of clapping and stuff. Sorry it couldn't be more interactive. Before I ask any questions from my end, I'd like to open it up for questions from the other speakers, from the other attendees. So please feel free to raise your hand on the Zoom. Yeah, go ahead, Chi.
Thank you, Kristina, for this wonderful talk. And I'm having a question regarding the video. So the videos they should be RGB, right? So they are not grayscale. The videos you show in the slides, right?
So actually, the videos have 4 channels, RGB and IR, and I'm just showing the RGB version of that. So one thing that we struggle with here is that, you know, a lot of the colors are missing from these videos, right? And the reason for that is as follows. Basically, at night, at the very darkest settings, we have the most signal from IR. And because of this like special Bayer pattern that we have, every single one of these channels has IR in it. And so, as I said before, we could maybe subtract out the IR channel and get back the RGB videos, but unfortunately, that's going to remove most of the signal. So while for certain like brighter images, we can see color, for a lot of the night images, we have very, very muffled colors. And so this is kind of an open problem of like, you know, how do we get back the colors? And I think like kind of the answer here is perhaps there's like some work that can be done in trying to just like make up the colors. So perhaps you can do some kind of like color in painting, for instance. But yeah, we definitely have a problem with like, you know, a lot of the color is gone, but that's just kind of a fundamental to this scenario where like you don't have much color information present in the first place.
Gotcha. That's exactly the question that I was going to ask you. Thank you.
Excellent. We have a few questions, so I'll just get through them. Nick?
Hey, Kristina. Nice to see this work for the second time in a week. I think it's really cool. I guess I was wondering, so you built this noise model, which I think is really cool. Did you try sort of more classic denoisers like total variation, but using like trying to build like a statistical model and use like classical approaches, but where you maybe assume each pixel has I don't know, like Gaussian noise, but that each pixel isn't identically distributed, if that makes sense. So, you know, use some kind of like weighted least squares term with total variation or some like classical approach. Not the way that you did doesn't make sense, but I'm curious if you considered that at all once you had the noise model.
I mean, I think like in general, so for the classic approaches, the best one that you can use off the shelf is probably VBM40, because it actually already works on videos. And, you know, for most videos, it actually works really, really well. And And then your question is, can we then like use something like total variation to help us out? And, you know, in practice, TV does not do as well as deep learning. And so we have this deep network, and we actually did try to use like some TV terms during the training, and it did not work so well, and it kind of blurred out a lot of the motion. And so to get the sharpest, cleanest results, we did not use TV essentially. So we found that actually TV was not helping us.
Yeah, that makes sense. I guess I was asking, TV is doing this constrained inverse problem where there's two terms. One is like an L2 difference between the denoised image and the ground truth. That comes from the Gaussian assumption. I guess I was wondering if you could modify that term based on your noise model. And if you think that would matter, right? Because like classic TV denoiser is assuming a noise model that doesn't fit your data. So it maybe makes sense that it wouldn't work.
Yeah, I think perhaps there is some way that you can hand design a more classic algorithm to work better with this. But I think what we've seen is that it works much better if you can just deep learn it, essentially. So if you have some more data, it usually will do a lot better.
I'm sure the deep learning would win. I guess I was just curious what the gap would be. But
I think there would be a very large gap.
Yeah.
Okay, Joshua?
Hi, Kristina. This was really clear and great to see. I guess I'm wondering about the input images. So are they demosaicked? And I guess this is sort of related to Chi's question, but like, I wonder if either the raw data that's not demosaicked would be easier to denoise, or if just like, because it's so hard to reconstruct the color, whether a monochrome one without like that captures IR and doesn't discriminate between any of the visible wavelengths would just be better at collecting more light too. I don't know, those are kind of two different questions, but trying to understand like why we see this particular kind of noise and whether you could just avoid it by avoiding the color filters.
Yeah, so actually like the raw input, we just use the 4 color channels. So we have like the 4 color channels going in for everything here. And so I don't think that really the noise is from the colors, because we are operating on the 4 separate channels. It's really just, it's fundamentally like from the gain that we're adding. So we have like this extremely high gain that we're operating the camera in, and that's causing most of this noise that you see. So yeah, I mean, I think like in general, if you had a monochrome camera, perhaps you can do a little bit better, but you know, there was some hope at the beginning of this project that we would be able to get more vivid colors, but unfortunately it didn't quite work out.
Right. Okay, yeah, that makes sense. Thanks.
Next question is from Hano.
Hi, Kristina. It's a great talk. Thanks, and very clear. I have one question. You have fixed pattern noise in your noise generator. So you train your noise generator on full frames, or are you able to use crops from the images? Just a fixed pattern would change when you crop.
Yeah, absolutely. Yeah. So we do train it on crops, but we keep track of where the crop is from. And so we use a fixed pattern basically. And so say if we're cropping it to like the lower right center, we basically like use the fixed pattern for that portion of the sensor. So we do have to keep track of that for the training.
And how did you do this? I couldn't follow that. How did you keep track of where you took the crop from?
I mean, it's just you can just do it in the code, like while you're feeding in the patch, the real noisy patch, you can basically just like also feed in an index of where it was cropped from. And then if you know where that is, then you know where the fixed pattern is as well.
But you needed to tell this to your unit, no?
Yes, yeah, that's right.
I think I'll ask you again on that offline, if that's okay.
Yeah.
Thanks.
Okay, next is from Katie.
Hi, yeah, Kristina. Fantastic talk, very impressive and also clever to think about dealing with the noise in that way. I guess I had a question about. So here you were working with a still camera and people were moving. I was wondering, like, if you start moving the camera itself, then things like fixed pattern, you're not always in the same location and everything. I wonder if you would gain anything by having a moving camera.
Yeah, so I mean, the fixed pattern will not change with the camera motion. It's basically intrinsic to the camera itself.
But I
So
meant
you'll see the
relative to
same.
where it lays on, like
Right,
where,
right.
yeah, what's it affecting in the image will change. Yeah.
Yeah, I think kind of the limit there was the fact that, you know, our camera is quite large and bulky, and we're taking exposures. Well, so we're operating between like 5 to 10 frames per second. And so it's really difficult to kind of like have this sort of smooth motion without any motion blurring during our exposure time, because our exposure time is still a little bit longer than we would like it to be. So it's kind of tricky to, you know, have your camera move just enough so that you don't see that. But yeah, I do agree that perhaps if we had some kind of better like motion stage for the camera, you could perhaps take a pan and get back like a really nice video from that. Unfortunately, we didn't really have that sort of hardware available at the time. So most of the images that we have, I did move the camera a few times, but there's just a lot of motion blur in all of the images from that. So it wasn't very usable. So yeah, I think that's a really great like future step where perhaps like given the right hardware, you could take a data set that actually also has motion in it as well.
Cool, thanks.
Awesome. So I get to, I guess, call on myself here. So really good talk and really clever to deal with the noise in this way, as Katie mentioned. I want to follow up. I have two questions, if I may. The first is technical, and I'd like to follow up on Nick's question about kind of how does the deep learning compare with classical methods? So one of the topics that I think I've been discussing with a few of our students here is like, we know deep learning does better. What are the types of artifacts, like in the limitation section, right? Like, you know, there are going to be failure cases of any noise method, this one included. Do you have some kind of qualitative characterization of the types of artifacts? So for example, a simple median filter for denoising will have artifacts on high frequency detail, and you can kind of interpret that. Do you have some intuition on what the shortcomings of a deep learning method are qualitatively?
Yeah, I mean, there certainly are going to be limitations. I think one thing that is nice about denoising is you basically are you're not trying to create new content. So a lot of the work that I've done before this project was dealing with inverse problems where you have like a very distributed point spread function. And there, I think I've seen a lot more cases of hallucination. And this sort of project here, I think it's really hard to quantify exactly what the artifacts are. And I think that's like a whole nother field really of like, you know, how do we make these like really, really robust, and how do we, you know, quantify if it's hallucinating anything? So I feel that like, you know, looking at these images, they certainly look very similar to the raw data. And I think one thing that's really promising is the fact that we're actually able to like see these stars moving. So we actually like, you know, we're able to see these like really fine detail sort of features going throughout the scene. So that's like something that like we're sure is actually in the data because we can see it there. So I mean, there isn't really a good answer to this. There's just like, you know, the network will probably hallucinate something. I guess I don't have an image of this, but one thing I saw is that there was like a tree in someone's hand, and the hand was very clearly above it was in front of the tree. But, you know, because the data sometimes is very, very dim, perhaps that the network might try to put the tree in front of the hand. So you might see like some weird things like this. But as I said before, it's really difficult to like quantify exactly where it's going to show up and what it's going to be. So I think that's like a whole open question.
Yeah, agreed. I think that ties in with all that interpretable deep learning stuff too. So it'll be interesting to see how that evolves. We're kind of at the end of the calendar invite, but if I may, I do have one more non-technical question. So the Grundfest lecture often has, and we'll do a better job of this as the organizers, of kind of having like a quick spiel by the presenter about like kind of what they wish they knew as a first-year PhD student in computational imaging, or what advice they may have for early-stage computational imaging PhD students. We won't, not to put you on the spot, Kristina, but do you have any wisdom you can share about your time as a PhD student that might be helpful for the junior scholars on this call?
Yeah, I mean, I would say that it goes by really fast. So to just take the time to learn at the very beginning. I would say also the thing that helped me the most was working with people. So I think it's really, really lonely and really, really hard if you're working on a project by yourself. So it's much easier to stay motivated if you have good collaborators. So I encourage everyone to try to find collaborators to work with, because it'll make the science much more fun and much better as well. So it's always good to have people to talk to about your work, because otherwise you might be kind of stuck in this hole where it's like you're not making any progress. But if you talk to other people, you might get out of that much faster. So just finding good people to work with would be my biggest takeaway from grad school.
Excellent. Thank you so much. So with that, we've come to exactly 1 o'clock. So we'll kind of end this.